Hello everybody, my name is Enrique García Macías from the University of Perugia in Italy, and I'm presenting this work entitled Statistical Process Control Procedures for Online Damage Detection of a Monumental Masonry Palace, the CONSOLI Palace in Gubbio, Italy. This is the outline of this talk. First, I would like to give you the motivation of this work. Afterwards, I will present a concise overview of the theoretical fundamentals of a damage detection approach proposed in this work. And finally, I will present some numerical results of two case studies, a simple supported beam and the CONSOLI Palace in Gubbio, Italy. So let's start with the motivation of this work. This work arises as a result of the long experience of my research group on the development and application of vibration-based SHM. Essentially, this maintenance strategy relies upon the installation of a set of accelerometers on a structure monitoring ambient vibrations. Afterwards, these acceleration records are used for the identification of the modal parameters of the structure, that is, its resonant frequencies, mold shapes, and damping ratios. And finally, we use these modal parameters as damage-sensitive features. Therefore, the key premise of this approach is that since modal parameters are directly related to the stiffness of the structure, if it experiences a damage mechanism, we will be able to detect it by tracking its modal features. Nevertheless, it has been well documented in the literature that these approaches must face a really challenging obstacle, that is, the effect of environmental conditions. Here I show a very famous example among the SHM community, which is the Zeta-24 bridge studied by Peters and Widow-de-Roeg. In that work, those authors investigated the correlation between the resonant frequencies, in this case the fundamental frequency in the y-axis, versus environmental temperature in the x-axis. In this graph, it is very clear that resonant frequencies are strongly correlated with environmental temperature, with ranges of variation that may be up to 15 to 20%. This results in a masking effect of structural pathologies whose influence is usually considerably smaller. In addition, these environmental effects might be highly nonlinear, such as in this case where we can observe that there are two clear trends in the data. Also, damage may affect these correlations as evidenced by Ubertini and co-authors in a masonry bell tower. In that work, damage assessment was performed using control charts after eliminating the environmental effects using a statistical pattern recognition approach. Here it is observed that before the seismic sequence of 2016 in central Italy, the control chart displays a stable distribution of data points. But after the seismic sequence, some fluctuations appear, indicating that the correlation between environmental factors and resonant frequencies may have changed. So in this context, it is evident that the effectiveness of a vibration-based SHM system for damage detection largely depends upon its capability to phase out environmental effects. So in this context, with the aim of addressing the normalization of the resonant frequencies of structures experiencing highly nonlinear environmental effects, we propose in this work a 5-step damage detection approach described by the workflow in the slide. It comprises the collection of ambient vibration records in a structure and the extraction of its modal features through automated operational modal analysis. The identified resonant frequencies are arranged in an observation matrix Y by columns. Here, a dataset is defined as the training period to define the healthy condition of the structure, typically a 1-year period. Then, in order to characterize the different environmental regimes in the structure, the resonant frequencies in the observation matrix Y are clustered together into different datasets using a Gaussian mixture model. This approach assumes that the probability density function Px of a dataset in the training period can be represented as a linear superposition of k Gaussian components or clusters. The model parameters, that is, the mean vector, the covariance matrix, and the distribution of the data points into the different clusters, can be obtained by minimizing the log likelihood function through an iterative expectation maximization algorithm. Once the resonant frequencies are organized into clusters, the presence of outliers is minimized by using the minimum covariance determinant method. This approach consists in finding an user-defined percentage of the data population that minimizes the covariance matrix.
To do so, the data points are sorted according to their Mahalanobis distances to their clusters, and those with maximum distances are eliminated. This process is defined in an iterative way until reaching the user-defined population size. So at this point, the dataset has been organized into clusters and the outliers have been minimized. So we can say that we count on a clean training population suitable for constructing an accurate statistical regression model. In particular, we use in this work the well-known principal components analysis, but with the particularity of being local in nature because we take advantage of the distribution of data points into clusters. This model basically consists in the Eigen decomposition of the covariance matrix of the training dataset organized into clusters. In this decomposition, the loading matrix U contains the principal components, and the elements of the matrix S squared represent the variance contribution of each principal component. Here we can assume that the principal components with the largest contributions to the variance represent the effects of environmental factors. Therefore, if we retain only a set of principal components in a reduced loading matrix, it is possible to reconstruct the original observations while keeping most of the variability due to environmental factors. This reduced loading matrix will allow us to predict the values of the resonant frequencies of the structure beyond the training period. So essentially, this loading matrix is a model that represents the healthy condition of my structure. And finally, once we have a statistical regression model characterizing the healthy condition of my structure, it is possible to investigate the appearance of damage throughout the analysis of the differences or residuals between the experimental resonant frequencies and the predictions of the statistical model. A common approach to detect the appearance of an anomaly, so in other words damage, in the time series of the residuals is the use of statistical control charts. This approach essentially represents certain statistical distance or metric between the resonant frequencies and the training population. Therefore, if a damage process initiates, it can be detected in the shape of an alteration in the statistical distribution of this statistical distance. Several different statistical distances or metrics can be found in the literature, but in this work we have used the Hoteling's t-square control chart and the multivariate exponentially weighted moving average control chart. Interested readers can find more information about these control charts in the conference paper. And now I show you some numerical results obtained with this approach. Specifically, we first investigated a benchmark case study of a simply supported beam with temperature-dependent constitutive properties according to this bilinear relationship in the slide. The first 4 natural frequencies of the beam have been used as damage-sensitive features, and a dataset of 3,330 data points has been constructed according to this table in the slide. It includes a training population of 1,830 data points comprising UZ1 and UZ2, followed by 5 different damage scenarios with increasing damage severity. The damage is simulated via reduction of the bending stiffness of the 4th element in the beam, and temperature values have ranged randomly between -20 to 40 Celsius degrees. Also, the presence of outliers has been simulated through a random variation of the mass density of the beam with a value of ±10% of the mean value all throughout the monitoring period, except for the second half of the training period where this variation range increases to 25%. Here I show the results of the clustering analysis where it is clearly noted that the data points corresponding to the 2 different trends in the stiffness of the beam can be separated well. Then the presence of outliers is minimized by using the minimum covariance method, and 2 statistical models using 1 single principal component per cluster are constructed. On this basis, we constructed the Hoteling's control chart with and without outliers elimination. It is observed that the model without outliers elimination cannot detect the damage until it reaches a reduction of the stiffness around 40%. On the contrary, the model with outliers elimination can effectively detect all the different damage scenarios. And finally, we go with the key case study in this work, the CONSOLI Palace. This historical palace was erected in the 14th century in the municipality of Gubbio in Italy and currently hosts the Civic Museum. As an extraordinary example of a complex masonry palace, this structure has been the case study for multiple research works, including the European Horizon 2020 project Heracles. A permanent low-cost SHM system with 3 accelerometers has been installed in the palace since July 2017 until July 2019. Ambient vibrations have been acquired using a LabVIEW code, and files containing 30-minute long records have been sent continuously through the internet to a server computer where they are processed in real time using a software program called MOS. MOS, which is the Italian acronym of Structural Health Monitoring, is an in-house software code for the management of integrated SHM systems. Here I show a promotional YouTube video we developed for showcasing the main features of this code. And here you can find a time-lapse video of the real-time SHM of the CONSOLI Palace, including automated operational model analysis and frequency tracking, and the construction of several control charts for damage detection. In this slide, I showed the results of the automated operational model analysis of the palace using covariance-based stochastic subspace identification. In particular, we found 5 modes in the frequency range up to 10 Hz, including 2 global bending modes, FX1, FY1, 1 torsional mode, T1, and 2 local modes, L1 and L3. Here, it is interesting to note that local sudden increases in the resonant frequencies are observed from February 25th to March 1st, 2017 due to freezing air temperatures. Therefore, it is quite clear that the relationship between resonant frequencies and environmental temperature is complex in this example, so the motivation for using the proposed damage detection approach is quite clear here. This is the result of clustering of the previous time series of resonant frequencies versus environmental temperature using 5 clusters and 2 clusters. In the 2-cluster model, data points are separated well between freezing and non-freezing conditions, although it is observed that data points without freezing conditions exhibit a highly nonlinear correlation with temperature, including certain hysteresis. These correlations are further discretized when using 5 clusters, where the branches of the hysteresis cycles are separated into different clusters. So we selected the 5-cluster model and eliminated 5% of the data samples considered as outliers using the minimum covariance determinant method in a training period of 1 year. The client training population is used to build a PCA model using 2 principal components. Here I show the resulting control charts in terms of Hotelin's t-square control chart and multivariate exponentially with moving average control chart, without and with outliers elimination. Damage is simulated in the shape of decays of the fundamental frequency of 0.4% for a mild damage and 1% for a moderate damage. Overall, it is observed that the elimination of outliers represents a substantial enhancement of the damage detection capability, with increases in the number of outliers in the Hotelin's t-square control chart from 10% to 16% for mild damage and from 15.6% to 41.3% for a moderate damage. Even larger increases are found in the multivariate exponentially weighted moving average control chart, what demonstrates the effectiveness of the proposed approach.
And this is all. Many thanks for your kind attention. Goodbye.